Welcome to the SBGrid YouTube channel. Software tutorials by developers, lectures by structural biologists, unique content brought to you by SBGrid.
Hi, everybody. This is Jason Key at SBGrid in Boston. Thanks for joining today. Before we get started, a couple of announcements. This is our last webinar of 2021. It is my pleasure to welcome Sjors. So Sjors is joining us from the MRC at the L&D in Cambridge. And Sjors is going to be telling us about what's coming in RELION-4.0. So go ahead.
Thank you, Jason. Thank you for the invitation to speak. It's always fun to speak at these SBGrid seminar series. So today I'll speak to you about the new developments that are in RELION 4.0, which we publicly released for beta testing 1 or 2 months ago. And we're still writing up parts of the stuff in there, and I'll speak about that as well. And another part has been or is probably in press now, but is already available on bioRxiv. So if you happen to follow me on Twitter, then you'll see that I often rant about how open software accelerates science. Everything we do is open source software. There are no limitations whatsoever on other people to do what they want with our code or our software. And we think that's an important part of having science progress as efficiently as possible. Cool. I thought I'd start by acknowledging contributions from the RELION team. So Takanori Nakano was a postdoc in my lab. He's recently started a new position in Japan, in Osaka, following his passion for electron diffraction. Derek Emanius is currently a postdoc in the lab. I'll speak about his work. Li Dong was a student in the lab. I'll speak about her work too. Scheres is a new student in the lab, and I won't speak about his work because he only just started. Then Joaquin Oton, or Kino as we call him, was a postdoc with John Briggs, has now moved to Barcelona in a more independent position. And Jasenko was a postdoc in my lab, who then moved to Basel to work with Henning Stahlberg. I'll speak about work from Kino and Jasenko as well. And then Johannes is a postdoc who recently joined, and I won't speak about his work. Now, RELION has had several contributions from outside groups as well. And perhaps the most important to note here are contributions by the group of Erik Lindahl, who's at the Scilab lab in Sweden, and Dari and Björn Forsberg from Erik's group made important contributions in accelerating RELION both for CPUs and GPUs. And then also the collaborative computing project in electron microscopy group, who's based at Harwell here in the UK, have recently made contributions. And as I'll talk to you about near the very end, we're working on a tighter integration with the CCPM software. Cool. So what people often ask me, what will the color be of the next version? So RELION 4.0 was chosen to have a strawberry color scheme, if you think that's relevant. Its new features are in 2 areas. So in the first one, sub-tomogram averaging has had a complete overhaul of how we do things. And this is work by Kino, who did part of rewriting, refactoring RELION Refine for that. And Jasenko adapted his algorithms for Bayesian polishing, CTF refinement, etc., to do those types of corrections on sub-tomogram data, and I'll speak about the details about that. Then there's a whole bunch of smaller developments that have improved what we hope is single particle analysis, and I'll go through those a bit later on. So in traditional sub-tomogram averaging, one would align a tomographic tilt series, then reconstruct very large tomograms, and then extract in smaller boxes sub-tomograms from 3-dimensional coordinates where you think your particles of interest are, and then those are aligned and classified and averaged to get a sub-tomogram average structure, which hopefully extends to higher resolution than the raw tomograms. Now, previously in RELION, we worked with Tanmay Bharat when he was in Jan Lowe's group here at the LMB. And what we introduced in sub-tomogram averaging in RELION already a while ago, in 2.3 or 2.4 it was the concept of a three-dimensional CTF, which kind of was thought to represent the signal transfer, the three-dimensional signal transfer in Fourier space. And because these were basically slices of the individual images of the tilt series, they also then corrected for the missing wedge. Now, that still didn't account for all the problems. And one problem was that the previous approach in RELION assumed nothing about the raw two-dimensional pixel values in the tilt series, but the statistical assumptions that were made were on the tomogram, on the 3D tomogram voxels. But of course, the raw data is actually 2D, and the concept of a 3D CTF isn't really correct. The CTF really lives in the 2D tilt series images, not in this kind of sub-tomogram space, 3D space. And the effects of these on the reconstruction then of the average were kind of ignored. That together with the observation that the tomograms themselves are often very, very large files, which are kind of bulky to handle and just inconvenient in general. Now, what we did was we came up with this idea of pseudo sub-tomograms, and I have to say we're not the only ones to do so, nor the first ones. I think there was this constrained refinement of tilt series images previously. What was that? Bartasagi, I think, and I think the similar concepts in M from Dmitry Tikhonov as well. But what we wanted to do is to use the raw tilt series 2D images and put them in a three-dimensional volume that could be fed into the code of conventional code of RELION Refine. But the 3D volumes that we give RELION Refine no longer represent a true approximation of the 3D density of the structure of interest. They are basically, you could think of them as a stack, but it's not a horizontal stack. It's a stack in a kind of wedged shape with overlapping parts of 2D images in the 3D Fourier transform. But we use this way of giving data to RELION Refine to then approximate the likelihood that would arise from working on the individual 2D tilt series images with the statistical assumptions of independent Gaussian noise on Fourier voxels now being close to those of the Fourier voxels in the 2D raw images. Now, if you want to do that, then because part of the tilt series images in the Fourier transform will, of course, overlap, and that's most noticeable at the line along the tilt axis, of course, but also at low resolution around that line, there will be a certain amount of overlap. So if you want to do this, approximate this as well as you can under these circumstances, then it's no longer enough to give only a 3D Fourier transform kind of with all these 2D slices in it and information about the CTF of those slices. You also need to bring along how often each pixel in the 3D Fourier space has been sampled by each of these 2D slices. Otherwise, you can't do these calculations correctly. So that's an additional term that has been added to the 3D pseudo subtomograms in RELION-4. Now, the advantages of this is that we now approximate at least a plausible statistical model on the 2D raw images, and by not just dealing with flat 2D image stacks, which would have required a complete rewrite of RELION-refine, we can now still use existing methods of refinement in RELION. So we've modified RELION-refine program to be able to deal with these images together with the multiplicity. And now you can use all the tools that are already there: 3D refinement, 3D classification, symmetry expansion, multi-body, etc. Using code that was already there, rather than having to refactor all of that. You can now another advantage of this approach is you can now reconstruct the average map conveniently straight from all the relevant areas in the 2D images of the tilt series. And the map that you generate can then be used as a reference to then optimize parameters of the tilt series, for example, the tilt angle and where the tilt axis lies, but also if there's beam-induced motion of individual particles throughout the series, this can be done in a way that is analogous and very similar to the Bayesian polishing that people use for beam-induced motion correction in single particle analysis. That then leads to improved 3D maps, and you can then make improved sub-tomograms, and the whole procedure becomes iterative. So RELION, if you have RELION 4.0 loaded in your SBGrid environment, and I understand from Jason this has now been installed, you can do RELION -- tomo, and you'll get a GUI that is specific for the tomogram reconstructions. So it has an import function, and you'll still need to do your pre-processing in third-party software. So I think Kino and Jacinko have mostly used IMOD, and they've written import scripts or import code to import from the directory structures of IMOD into the RELION framework. And I've seen on Twitter that other people have been working on doing this for other softwares as well. I think I've seen something for M come around in the past few weeks. Now, then you generate these pseudo sub-tomograms from the aligned tilt series images. So this will basically read in the tilt series images and then take the relevant areas for each of the particles and the relative CTF, taking into account in what height in the Z in the tomogram you are, etc. But you do need for this three-dimensional picked coordinates in some raw tomogram that you've made in that third-party software. That could, however, be in a downsampled file, which would be less big than the full resolution. So, and then creating sub-tomograms is a bit like extracting particles from single particle analysis, and there is a GUI functionality for that. Those sub-tomograms can then either go in 3D classification, or, for example, if you think your data is homogeneous, you could run a 3D auto refinement with two separately refined half maps. And there is a slightly adapted version of the GUI for that as well, but most of it will look very familiar from those of you who have used RELION for single particle analysis. Now, the refinement of the sub-tomogram will now lead to better angles and translations for each of the individual particles. And you could use that to reconstruct a new map, or you could use the map that RELION-refine gave you directly as a reference. And then you can do what we call tomogram frame alignment and tomogram CTF refinement. And the frame alignment is as I told you before, the equivalent of Bayesian polishing. So you can set fit per particle motion no, then it will basically do a tilt series realignment, but now comparing the individual parts of areas of each of the particles with projections of the 3D reference map. So you can hopefully do a better job than the original tilt series alignment. Or if you set this option to yes, then you can follow beam-induced motion throughout the tilt series, and it depends on your data whether how much that will help you out. And then analogous to CTF refinement in single particle methods, you can do the same with these sub-tomograms as well. So you can do a defocus refinement, which is probably the most useful aspect of this. Often the height of the defocus is kind of off for individual particles, but you can also refine higher order aberrations, just like we do for single particle analysis. Now, for these to really matter, you either have to have a lot of beam tilt, which wouldn't be a good thing, but if you have, then you can correct for this, or you have to have really high resolution in your sub-tomogram average, because otherwise often you don't get to resolutions where this really becomes a problem. But as methods progress, etc., we think that the higher order aberration correction will gain in importance too. And as I said, this becomes an iterative process because the refinement leads to better angles and offsets, and then the frame alignment and the CTF refinement leads to better tilt series alignment, beam-induced motion tracks, and CTF parameters like defocus or the aberrations. So you can go back and forth. And just to show you some results, this is Kino did this on a test data set of immature HIV, which comes from the BRICS lab, has been used in multiple papers. And we just used particles from 5 tomograms, and going from an initial refinement just in RELION-4 with pseudo sub-tomograms using some initial model that I think Kino made from de novo from the particles, or he got just the one that the structure that was there low pass filtered. But if you don't do any of the fancy new stuff, already RELION gets to 3.6, which I think already outperforms RELION-3. But you can then do CTF refinement, frame alignment, another 3D refinement, and do this cycle 2 or 3 times. It converges to about 3.2 angstroms, which is pretty good for this very small data set. Now, the paper on this has been delayed because of COVID-related and personal reasons. So please bear with us. I still hope to have it out on bioRxiv in a few weeks, perhaps only with limited results while we work on more of the results. But yeah, that's still in the pipeline. So stay tuned for that. Then on the single particle analysis side of the RELION-4 release, we have multiple contributions. So I myself wrote based on popular demand here at the LMB, I wrote a wrapper for Topaz because many people were using Topaz for auto-picking. So I wrote a wrapper for auto-picking of Topaz, and then also implemented a wrapper for denoising of micrographs. But after actually speaking with Alex Noble, and he said, oh, why don't you do denoising as well? So just as we don't know, Topaz is this neural network-based picking program, positively unlabeled. So you don't need to pick all the particles as kind of initial templates. You can get away with just a few. It was done by Tristan Babler and Bonnie Berger's group, and Alex Noble was tightly involved as well. So you can now if you do manual picking, you get the typical kind of long GUI with a pick button for each of the micrographs. If you say here, you could previously already low or high pass filter those micrographs. If you now say here, yes, use Topaz denoising, and you don't have to tell RELION where Topaz is installed, then you will get denoised micrographs to manually pick your particles in. Just to give you an example, I think this is a ribosome data set. On the left is the raw micrograph, and on the right is what you just get with default parameters using Topaz denoising. So that can be quite useful if you want to look for very small details or specific things in your data set. And then Topaz-based auto-picking, there's now a tab which is called Topaz, which complements the Laplacian of Gaussian tab and the reference-based auto-picking tab. So Topaz, you can perform training. So if you set this to yes, you can do either manually pick coordinates from, for example, the manual pick job that I just showed you, or if you have a set of particles that you've selected, perhaps after 2D classification of log pick particles, you can also train Topaz with this set of particles from the start file. And you do either training or picking. So if you set picking to yes, then you can pick. If you don't provide a trained model, then it will just use the default Topaz model. And if you want to train it yourself, or have trained it yourself, you will have an output file, which is the Topaz model, which you can then input here and use that to specifically pick your own data set. Just an example. This is a auto-picked micrograph with Laplacian of Gaussian. You get these typical false positives here around these artifacts. And what we did 2D classification of all the picked particles, select good classes, and then use all the good particles to train Topaz, and then do retrain Topaz picking. And these are the picks from Topaz. So some of the artifacts are gone, although probably it shouldn't have picked this one. So that can be very useful. We've used this Topaz framework ourselves in several settings, and we think we're quite happy with it. Then Dari Kumanius, one of the students from Eric Lindahl who did the GPU acceleration, then became a postdoc with us, and he developed a new gradient-driven algorithm for both classification and refinement. Now, this kind of compares with stochastic gradient descent optimization as Adam compares to SGD. So there's an online estimation of the current noise level, and you get the second moment of optimization involved in the optimization as well. Now, the lawyers at the MRC who had given me previously a very hard time about implementing stochastic gradient descent in previous versions of RELION because of patents because of patents from the Structura company, they now are happy with this, and they say it's different enough to not involve with to not clash with these patents anymore. So they're happy with our current code that it wouldn't put the MRC in any problems. And I just that means that now again all our software is completely open and usable by anyone. So it doesn't matter if you're academic or industrial user, you can use all parts of RELION without any restrictions. So we typically run this new algorithm with 50 to 100 iterations, and it is important to say that each iteration now is a mini batch in the gradient descent algorithm. So these iterations are from much smaller subsets of particles, as would be from the expectation maximization algorithm, where you would loop through all the particles. Looping through all the particles is only done in the last iteration, and that makes the algorithm basically much faster, especially for large data sets, than the EM algorithm. Not only that, we also see that the VDAM, as we call it, algorithm generates much more different classes than the expectation maximization algorithm that you're all used to. So that's shown here. The top two rows here are classes from a membrane protein that are obtained using the EM algorithm, and the same data set with the VDAM algorithm gives classes, many more classes, different views, as shown in the bottom 4 rows, together with the observation that using the default parameters, the speed up is about a factor of 5 or 6 compared to the EM algorithm. That's if you use the kind of defaults. You can go down and use a bit lower iterations in many cases with the VDAM algorithm, because we've tuned it to be relatively robust to a large number of data sets. But if you see for your data sets, you can use half the number of iterations, you'll be even faster. You might be a factor of 10 faster than the EM algorithm. This is another example. I think this is the one from Gabe Lander. What's it called? I forgot about it, but same thing here. You get the classes from the EM algorithm, and then you get many more classes from the VDAM algorithm, and you get these much faster. So here at LMB, the VDAM algorithm is rapidly gaining popularity. Then Lee and Dari also contributed to this work on automated selection of 2D classes in RELION. And this is based on the observation that many people like 2D classification as a way to screen the particles, kind of get an idea of how the particles look, but also to throw away particles that are not good, and then take smaller subsets further into 3D refinement. Now, because we were interested in automating through the entire pipeline, this is kind of often, has always been a manual selection step where the user actually has to click on the nice 2D class averages, and that then becomes a stumbling block for automated procedures. So already for about 2 years before Lee started her PhD, and then for another 1 or 2 after she started, I had been asking RELION users through a little snippet in the code, every time they did a 2D classification and then did a subset selection, I would ask them with a pop-up window, would you be willing to share your images with us for algorithm development? And many people clicked yes, and then the 2D class averages and all the metadata from RELION Refine that led to that classification were copied to a directory that I owned. And doing so, we collected, I think, over 25,000 2D class average images. And Lee went through these, and we threw away redundant ones. We kind of wanted to have a more or less okay-ish distribution over different types of molecules, different sizes. You know, you might imagine with Venki here, there was lots of ribosomes and we didn't use all of them, etc. In the end, we used a total of 14,693 2D class averages with the metadata from RELION Refine. And then Lee sat down for a while and interpreted their quality on a continuous quality scale or semi-continuous. She had multiple classes ranging from very good to bad, and then some weighting with molecular weights, etc. But basically, we hope to have a continuous scale of 0 meaning very bad images. You don't want to include these in your data, and 1 being very good images. Now, then we designed a convolutional neural network, which is a combination of a standard kind of convolutional neural network, which also then concatenates at some point with 18 features, which we handpicked. And some of these are just metadata that come out of RELION, so the accuracy of alignment, accuracy of rotational and translational alignment, how many particles are in each class, etc. But also some of the features were calculated by Lee based on dividing the density into protein and solvent areas and for example, calculate moments in those as an attempt to kind of help the neural network to do better. And in the end, we then trained this whole neural network to predict the score for each of the 2D class average images using the manual annotation that Lee had done of all the scores on the training and the validation test sets. And this is just a kind of 2-dimensional histogram. So we have labeled scores from 0 to 1. There's lots of 0 images in the data set, which are basically all the kind of junk classes that people typically discard. But then there's a reasonably okay-ish distribution over the continuous score of the labels. And here on the left is now the predicted score, I think on the validation set. So there's a subset of 5,000 images that was not used to train the network. So you can see we do a reasonably good, the network does a reasonably good job at predicting the score that Lee also assigned to these class averages. And there's just some randomly chosen examples of class averages from the data set with their assigned, no, I think they're learned prediction in the top left and the bottom left here. And we just compared, you know, is this adding these 18 features in, is that a good thing, or is it not necessary? Is the network, the convolutional part of the network, is that good enough? And we saw we actually do get better mean squared errors on the loss if we use the approach with the features. So we decided to keep them along. So this has been implemented inside the subset selection job type, where there's now a class options tab, and you can say automatically select the classes, and then you have to provide a minimum threshold for selection, and you have to provide a Python executable, which should have access to PyTorch, because that's what we implemented the network in. And because we've kind of installed Topaz anyway for the auto picking, we actually use Topaz's Python for this, but you could use any of the other Python installations you may have. Now, the idea of having this threshold is because you as a user will know best at what stage of the particle selection you are, whether you still want to be more permissive or whether you want to be really restrictive, and also how good your data is expected to be, for example, based on the molecular weight of your particle. If you're working with ribosomes, then you probably want a relatively high threshold for selection. If you're working with a tiny membrane protein that is very hard to align, then you will probably want to drop the threshold. So that's kind of the flexibility that the software gives you. That was the whole idea of using this continuous score rather than a single good or bad classification, which have been proposed by others. Now, how does that work? So we tested this on 12 data sets that we downloaded from Empire, including large things like the ribosome, but also including quite small things like aldehydes. That was the one I showed previously from Gabe. Gamma secretase, for example. CB1 is the membrane protein that I just showed you some 2D class images as well. So in black, you can see the percentage of auto-picked particles versus, so the black is if you've auto-picked your particles, then you do a 2D classification using the VDAM algorithm, and then you manually select all the good classes. So this is a subjective thing that Dari and I did together, and then it depends on how many junk particles there is in each data set, whether you keep like 70% here or only 30% for gamma secretase, where picking was way too permissive, if you like. Now, then in orange is the number of particles selected after automatically selecting the good 2D classes using a threshold of 0.15 in RELION 1.4. So this is a fixed threshold, and it's the same threshold that's the default in the automated pipeline I will discuss shortly. And then you can see for the ribosome, it picks a bit too many. For TRPV1, picks a bit too few. For apoferritin, it's actually doing very poorly. But then for those picks, you can then analyze what's the false negative rate and the false positive rate based on the manual selection being ground truth. So you can see that for several data sets, you're doing quite okay. For example, here, Volta faceplate ribosome data sets, the false negative and positive rates are very low. So you're basically doing the same pick. For this virus data set, you pick a bit too much. So there's a false positive rate, but there's hardly any false negative, etc. But as you can see, for several data sets, there's quite large false negative and false positive. So if you just use the standard default value, then that might not really reflect the quality of your data set. So, and therefore, I also show the number of particles picked here and the false positive and negative rates for a threshold that is chosen specifically for each data set. So we kind of just chose the best threshold, giving the best false and positive and negative rates. And then you can see the worst the automated selection does is about 25% false positive, and all the other rates are smaller than that. And here's the values of the supervised D threshold that we use. For example, the ribosome, I told you, you can get away with a much higher threshold than some of the smaller molecules like gamma secretase or TRPV1. Cool. Now, with that in place, we could then think about doing fully automated reconstruction from data sets that, for example, are being acquired on the fly. And to do that, people have used the schedules in RELION 3, and they would set these things up manually and then run iterative schedules. Now, we've changed these schedules. We now call them schemes. They're a different thing from the schedules. The schemes is basically a framework where you can organize a whole set of jobs to be executed automatically, and the framework itself can take decisions. So based on parameter values in the script, which changes the thing as the thing goes along, you can decide to go into one branch of a graph or another one. So you have you can have a complicated branched graph to do different things in different circumstances, which is executed automatically from a little GUI that I will show you in a minute, which is called RELION-int.py and the RELION scheme GUI.py. Now, if you would open your the typical RELION GUI alongside that, then you'll see that magically jobs will appear in this as running, and they'll finish, and a new job will appear, etc. So this runs kind of separate from the main RELION GUI, where the old schedules would run inside of. Okay. Now, for what we hope will happen is that the scheme architecture is very flexible, and you can design your own branch decision trees, if you like, and iterative loops inside these with as much flexibility, hopefully, as you need. And for that, we have this concept of job types, which is just a typical job types in RELION, so import, CTF find, motion core. But we also have what we call operators, and they are here in white ovals. For example, if you've been going longer than a certain number of hours, then just exit, things like that. Would wait for so many seconds if it hasn't waited before. So this would be an iterative loop of just doing import, CTF find, motion core. And this we call the prep scheme. It's a example scheme that's distributed with RELION as part of RELION-int.py for automated processing. But as I said, you can edit these and make your own for your own system. We have this does pre-processing, so just doing CTF find and motion correction on all the micrographs. Oh, this should actually be the other way around. The processing scheme is more complicated. It will see if you've done already some CTF find from the prep scheme. If you haven't, then it will just go back and wait until that's there. If you have, then it will select micrographs. It will do this just based on the minimum resolution from the CTF find, estimated CTF find. It will count how many there are. And if there's more than you had the previous round, then you'll go and do auto picking on the new micrographs. Then all the particles you have until then will be going into 2D classification with the VDAM algorithm. And you'll then do this auto selection of the particles using Lee's approach. You then count how many particles you are. And if a certain minimum has been obtained, then either you've provided an initial model, or in which case you just do straight refine 3D event 3D, or if you don't have an initial model yet, because this is the first time you're here and you haven't provided one on the initial GUI, then it will do initial model generation for you, which now also works using the VDAM algorithm from DARI rather than the SGD approach that we had before. And if any of these conditions is not met, then you just go back and wait until more micrographs have been pre-processed. So that kind of gives you an idea. You can do these complicated things, and what I hope is people will use this framework to adapt these things for their own systems. So this is what the RELION-int.py GUI looks like. So if you type RELION-int.py from the command line in your project directory, you get this this GUI. You can do micrograph pre-processing and or the particle processing. The particle processing uses the GPUs, which you need to specify here. And then you just specify where your movies are, your typical parameters of the microscope experiment for the pre-processing. And for the picking, refinement, etc., you just specify how big your particle is. You then get automatically a suggestion how big your box size should be, and there's actually works with downsample box sizes to just go and get your results more quickly. And you provide the symmetry as well. Then your resolution cutoff for the micrographs, and then you can either do log picking, in which case you need to provide a ratio of how your shortest and longest diameter of the particles are. Just use one if you think they're more or less spherical, and a threshold for the log picker. And if you use Topaz, then the algorithm will just use the default Topaz picker. Then this is the threshold for the 2D class selection that I just described for Lee's approach, and then how many particles do you want for your first 3D refinement, which the default is 5,000, and then if you type none here, then it will the first time it will run an initial model generation, and from there on use models used that way. So if you then hit save and run, this will just start launching all these jobs. They will be added to your pipeliner, and you can follow them in the RELION GUI. And we've written, one other thing that Grigory Scheres from the EM facility has written is this GIFI called Mdcatch. And this is installed on the computer that has access to the microscope computer. And this serves to capture all the metadata automatically from the microscope computer, and using either EPU or RELION, and then you can run this pipeliner in the schemer that I just told you about, the prep and the proc schemes, automatically in RELION. And then Grigory also wrote a version to run not only with Topaz and log picker, but also with Crayola picker. But you kind of give similar parameters here, and the rest gets kind of automatically gathered all from the microscope computer. So if you're interested in this software, it's distributed separately from RELION by Grigory, and you can download it from his GitHub account. So if you would run the either this system through Mdcatch by Grigory, or you run it just on the command line using the RELION.py GUI, then you can follow the process of the different schemes. So you can run this little GUI called RELION schedule GUI.py, and you can run it both on the proc and the prep scheme, and it will tell you whether this scheme is actually running, and you can, if it is, then you can abort it, and if it's not running, you can restart it at any point. So you can, this is a pull down menu, and you can restart at wait or at CTF find or wherever things went wrong. So if you see that you're running the whole schemer, but then you realize, I should have used a slightly lower threshold, for example, for the 2D class selection, because my particles are not as good as I'd hoped. You can just abort the processing pipeline, go to, this is a pull down menu of all the jobs. You can go to the particle select job and select the option of the threshold. This is another pull down menu, and just say if it was 0.15, but you now want 0.1, you just set it here. And then if you do restart, it will just, all the jobs that depend on this job with the change parameters will all be rerun automatically into new jobs in your pipeliner. So that's a big advantage of the way we did schedules previously in RELION, is you can now abort and restart in a very flexible manner, which hopefully will be useful for if you look at these things and realize you've made mistakes. Because previously what many people did, they realized they'd made a mistake, they just start the whole thing from scratch again. That's no longer necessary. So we applied this automated pipeline to those Empire data sets. And these are just resulting maps for all the different structures. So all of the structures, ironically, except for apoferritin, which is a data set used for the free align tutorial, which didn't go well at all. But all the other ones went well. And this was a case of very close neighbors, and the 2D class selection basically failed to select enough particles. It's a very small test data set as well. Cool. Then the last thing to mention, this is not really a feature of RELION-4, but the RELION-4 pipeliner structure itself has been simplified a bit in terms of what are the nodes and the edges, etc., compared to the previous versions of RELION. And also, whereas we previously used integer numbers, we now use strings in these star files, which are hopefully easier to interpret by humans. And Matt Yadansa, Colin Palmer, and Paul Burnley at the CCPM team, and especially Matt, who's done all the groundwork here, have come up with an ontology of what would be good names and what would be good hierarchy. And the idea now is that they built on the RELION pipeliner from RELION-4 to make a CCPEM CCPEM-pipeliner. And this is a project that's partially funded by a global phasing company from Sjors, who the X-ray crystallographers will know well. And the idea here is that in the long run, and hopefully a first version will become available for testing perhaps in 2022, if not 2023, then what we foresee is there will be a CCPM GUI that you can use to run RELION from, and in the same type of pipeliner approach that you're used to from RELION, writing out star files of RELION that are compatible with RELION. But the CCPM software suite is much wider than RELION alone. So Matt and Colin have been working hard to implement job types for all kinds of different things as well. And the idea is that CCPM will really become what it's intended to be, a collaborative computing project, as a kind of software marketplace with a single GUI, which you can run all kinds of different academic softwares from. And hopefully that will help to combine running jobs from RELION, perhaps with jobs from SysTem or jobs from EMAN or whatever we could convince to invest a bit of time to implement these things in the CCPEM-pipeliner. So we're excited about that. Under the hood in RELION, things are ready for this, and it's now at the CCPM team working hard to make this into something that will actually become reality. Then the last thing I think I wanted to tell you is that the RELION documentation has changed. So this was previously hosted in a wiki on the LMB website. We've moved to a GitHub repository with the documentation where we can easier make changes and track what has happened in the past. And then these documentation pages get compiled automatically on a website called relion.readdocs.io. So you'll see it looks a bit like the wiki, but there's a lot of more information. Make sure in the bottom right corner here to select release 4.0. That's not the default if you come here, because RELION 4 is still in beta, but if you select 4.0 here, then you'll see you have also a sub-tomogram tutorial that Kino prepared, where he goes through that entire 5-tomogram data set of the immature HIV capsid, which hopefully will be a good way of kind of getting to use the pseudo sub-tomograms in RELION 4 for your own projects too. Cool. That is it. I just put up all the people involved again. Rafaelero at the CNIO in Madrid has been quite a lot involved with early testing, so we're grateful to him. I thank Giuseppe and Grigory from the LMB EM facility, especially for all their work, kind of making the whole on-the-fly processing work at the LMB, which is now really up and running and people are using this. My thanks to CCPM and Global Phasing for the project with the pipeliner, and Jake and Toby are our high-performance computing scientific facility officers who help make sure we can run all our calculations all right. I thank you very much for your attention. I look forward to your questions.
Great. Well, thank you very much. If you have questions, you can use the reactions feature to raise your hand. It'll pop you to the top of the list, and I can unmute you and you can ask your question. I also have a few that I have here by chat. I also have to say, I didn't expect to see global phasing in the mix today, so that's pretty cool to see. Like at this point, all of the X-ray packages have, I like to see that line blurry, the X-ray, structural biology, cryo-EM. That's fantastic.
And so do they.
So, yeah, that's great. From the chat earlier, William Rice asked for the sub-tomogram polishing. Does the frame alignment have to be done within RELION?
So I think the only other software that would be partially compatible with this would be AM from Dmitry Tegunov at the moment, but I'll be happily corrected. So whereas AM has been written to work with sub-tomograms as they were formulated in RELION 3, I can imagine that if Dmitry would modify M to be able to work with pseudo sub-tomograms in RELION-4, then he would gain from that, but because the alignment and averaging would be better in RELION-4, and then people could do a hybrid approach like they do now, and with RELION-3, they could then do and with RELION-4. I think it would be quite hard to kind of go around and do your own type of polishing. Tilt series alignment might be easier, but do the whole type of polishing outside in your own scripts would become quite complicated, I can imagine.
Yeah. I had one more. Let me see if I have any hands up here. Let's see. Feel free to raise your hands and we can unmute. People can ask, but I have plenty in the chat too. So this one was from Pranav asked this, from Pranav Shah, who was a question I also had. If users want to incorporate their own 2D classes into training, like if they had, they were collecting on certain common samples, or they wanted to train on 2D classes, is there a way that they can train their own or enhance the training based on their own data?
For the 2D class selection?
Yes.
So not in RELION-4, not in its GUI, but Dari has put our entire network on GitHub, and we've sent all the information we've used for training to Empire. So there is an Empire entry, or there soon will be. I don't know if it's come out yet, but which has all the 2D class, all the 14,600 2D class averages and the metadata that we used for training. So one could then set it up, but it wouldn't be as straightforward as kind of retraining Topaz like you now do in RELION-4 GUI. And the reason for that is because the PyTorch integration with RELION is not there really yet. So we're calling just Python from Topaz to do some of these things, but actual training would want to use the GPU, and setting all of that up might be a bit complicated. So we're working on much more extended machine learning algorithms right now. So Scheres and Johannes and Dari are all working on those types of algorithms. So in the future, we'll come up with something which is it's more integrated with PyTorch.
Yeah, the current configuration works well with the Topaz. I can say that the Topaz Python underneath with the PyTorch, it works nicely. So it's
okay, cool. That's good too.
Yeah. It's a so I have another one here for the sub-tomogram averaging in RELION-4. This question was from Jean Jia, and it's a little detailed, but to understand the weight for each sub-tomogram in particle extraction, is it rectangular rather than the same dimension as the sub-tomogram? And the defocus of high tilt images for some tomograms can't be determined accurately. How to solve this problem?
Right. So I'd have to check. I think the multiplicity is stored together with the CTF in one file, but I'd have to check actually with Kino the exact implementation. I would have to look in the code. And then yes, if you have high tilt images, then CTFs are very probably quite poor from the standard type of IMOD CTF estimation or CTF estimation. Now, the whole idea is that should become better in this iterative cycle. So you just use whatever you get there. Don't worry too much about it. Do your first refinement, get a 3D average, which is much higher resolution, and then use the defocus refinement in the CTF refinement job type to adjust these CTF values. Hopefully, a few cycles of that will bring those defoci, which might be wrong, back to more correct values.
Great. If there are any other questions, feel free to raise your hand. I just disabled the unmute yourselves, so I think it's unlikely we would get Zoom bombed toward the end of the meeting here. So if you have a question you'd like to unmute, you can go ahead and do that. I had one other, well, I have a few more. One is based on the, let's see, got a long series of chats here, so bear with me a little bit. It's the, but besides the improvement of the 2D classifications for single particle that you were talking about, any 3D refinement improvements? Any?
Yeah, so the VDAM algorithm can work just as well on 3D as in 2D. So already we implemented now by default for the de novo initial model calculation. Now we've kind of played with it for 3D classification, but the advantages of speed and many more classes are not so obvious for 3D than they are for 2D. So you can use it. You would have to use additional arguments on the 3D classification job type, which you could get from the node file from the 2D job. But we thought it wasn't good enough to include yet on the GUI, although we will continue exploring that. Now, 3D refinement is something that is on our list to do, and you could have similar speed up factors there probably, but it's not completely there yet. So hopefully in the next release. And then also we've used, this is another paper by Dari in the IUCR journal, International Union of Crystallography journal from last year, where we use a regularization by denoising to inject a lot more prior knowledge in the reconstruction process. And it's a beautiful mathematical framework to do so is presented in that paper. And we think that would work particularly well with the VDAM algorithm in 3D Refine as well, where you have much more update steps. So, but this is something we're still working on, and that would probably, hopefully become part of RELION 4.1. So.
Great. One last question here as we get close to one. So can we do tilted series alignment and Tomo reconstruction in RELION_Tomo in the future?
That's a good question. I hope so. So John Briggs has just left. He's now started his lab at the Max Planck Institute in Martensried. And we're waiting for Tanmay Bharat to arrive as a new group leader here in the division. He will be sitting right next to me here. And with that, we'll have another group really interested in also in methods development in tomography. So hopefully together with some of Tanmay's people and perhaps some of the other people who are in the building now already, we can work on this, because it would be probably a lot easier not to have to import, because that's where things go wrong, right? People run IMOD slightly differently, and then the scripts don't work, etc. So this is, and we're aware of that. It's an Achilles heel, but it requires re-implementations of things that other people have done first, and we need to find somebody who's willing to sit down and do those. But yeah, it's on my wish list.
All right, great. Well, with that, Sjors, thank you very much for a great talk. Thank you for continually pushing and developing RELION 4, and thank you for championing open science and open source software, because I think and showing the power that open source software can bring to move everybody's science forward. It's fantastic.
Thanks a lot, Jason, and thanks for hosting. It was great as always.
Great. And so everybody else, have a great holiday. Have a great new year. Join us in 2022. Looking forward to seeing you then. Thank you.